to section 7.4, areas in polar coordinates. So you might look at this formula for area and say, where the heck does that come from? And that would be a good question. So to answer that, let's just back up a bit and talk about finding area in Cartesian coordinates. So if you recall, when we found areas in Cartesian coordinates, what we did is we approximated the area under a curve with rectangles. The height of each rectangle was y, and the width was delta x. So in the Riemann sum, we get height times width, the integral from a to b of f of x dx. And a and b reflect the places on the x-axis where the region begins and where it ends. Now contrast that with polar coordinates. When we have an area and we want to approximate the region with polar coordinates, we use sectors. And so you can see sectors look like slices of pie, and you can see I've got them fanned out here. The area of a sector is 1/2 r squared delta theta. And so that's where that 1/2 r squared comes from. And the d theta in the area formula is coming from the delta theta when we take the Riemann sum. Now, also one thing to note is the a and b here reflect the starting and ending angles of theta, where that region starts and where it ends. So in this picture here, this would be theta equals 0. And up here, this would be theta equals pi over 2. So let's just jump in and do an example. Find the area of half a circle, r equals 4 sine theta. And we already know that the answer is going to be 2 pi, but let's just verify it using this polar area formula. So I've started this out and I've got the integral written down. Now, where did I get these limits on theta, 0 to pi over 2? Well, when we start this circle here, here's theta equals 0. And when theta is pi over 2, I'm up here on the positive y-axis. And so that will give me exactly half of the circle. All right, and then I squared r to get 16 sine squared theta. Now, in order to integrate sine squared or cosine squared, we're going to need the half angle formulas. And so let's just review those over here. Sine squared of theta is 1/2 minus 1/2 cos 2 theta. And cosine squared theta, it's the same thing except with a plus in it. Okay, so this is the integral. First, let me combine the 1/2 and the 16. I've got 0 to pi over 2, 8 sine squared theta d theta. And if I use the half angle, that's 0 to pi over 2, 4 minus 4 cos 2 theta d theta. And now we integrate 4 theta minus 2 sine 2 theta, evaluated between 0 and pi over 2. And that gives me 2 pi minus 2 sine of pi. And then when I put in 0, I'll just get all zeros. Sine of pi is 0, so indeed I get 2 pi. Okay, let's do another one. Now, a comment about polar curves. I do expect you to know what r equals a sine theta looks like. That's a circle oriented on the y-axis. And r equals a cos theta, circle symmetric on the x-axis. And I've already expressed that those are just basic polar curves that you should know. In terms of roses, no, you don't have to memorize that. So I just went ahead and graphed this rose on Desmos, and we want the area of the half petal shaded over here. And so I've set up the integral 1/2 0 to pi over 4 of cosine squared 2 theta d theta. Now the question is, where's the pi over 4 coming from? So we can see clearly the beginning angle is theta equals 0, but the petal ends down here when r is 0. And so I want to set r equal to 0 to find out where that petal starts out. It fans, different values of theta. R is getting smaller and smaller. Where is it going back to the origin? So we're going to set cos 2 theta equal to 0. Now, that means 2 theta has to be an angle where cosine is 0. Cosine is 0 at pi over 2, at 3 pi over 2, ... Divide both sides by 2. That gives me theta equals pi over 4, comma, 3 pi over 4, comma, ... So this angle here is theta equals pi over 4. Now the 3 pi over 4 is over here, and that reflects where r is 0 again. All right, so there's our setup. So let's just go ahead and, well, you should pause the video, integrate, and see if you get pi over 16. This is, hopefully you did that. This is the integral from 0 to pi over 4. I'm going to use the half angle, and when I do that, I'm going to get a 1/2 from this, which I'll just pull out, group with that other 1/2 to put a 4th outside, and then I'll have 1 plus cosine. You have to double the angle, so the initial angle is 2 theta, so this will be a 4 theta. You could also leave the 1/2 in there, that's fine, either way is fine. So this is 1/4 theta plus 1/4 sine 4 theta, evaluated between 0 and pi over 4. Okay, well that's 1/4, and then I get pi over 4 plus 1/4 sine, again, of pi. And then when I put in 0, sine of 0 is 0, so everything's going to zero out. And so this is indeed pi over 16. Okay, just like in Cartesian coordinates, if we have two curves, an F and a G, and F is on top and G is below, and we want the area of the region bound by F and G between A and B, we can generalize the area formula in Cartesian coordinates to get A equals the integral from A to B of F minus G dx. Well, we can generalize the polar area formula too to get 1/2 integral from A to B of big R squared minus little r squared. So let's do an example. Here we're just going to do the setup. So we want to set up an integral for the area inside of the circle r equals 4 sine theta, and above the line r equals 3 cosecant theta. Now, how do I know that that's a horizontal line? R equals 3 cosecant theta. Cosecant is 1 over sine. Multiply both sides by sine. R sine theta is 3, but r sine theta is y. So that's the line y equals 3. So to set up my integral, I need to know the value of theta where those two curves meet. So I set them equal to each other, and that's what I've done here. Multiply both sides by sine to get sine squared. Theta is 3/4. Then I have to take plus or minus the square root of both sides. And so if sine theta is plus or minus root 3 over 2, I want angles in quadrants 1 and 2. So the first place that's going to happen is pi over 3. And the second place is over here at 2 pi over 3. So now I can set up my integral. It's going to be 1/2, I'll put that out front, and an integral from pi over 3 to 2 pi over 3. I want big R squared. My big R is the circle. This is big R. Little r is the line. So big R squared is 16 sine squared theta. Little r squared is 9 cosecant squared theta, d theta. Okay, now one thing I want to point out, you could evaluate that integral. So we're done with the setup, but in terms of evaluating, you could evaluate that, but it would be easier to introduce a quadrant angle and use symmetry. So I'm going to write, or what if we found the area of just half the region and multiplied our answer by 2? Now the advantage that would give us is when we evaluate the integral, one of our limits would be pi over 2. Quadrant angles are always easier to work with. So I could say twice 1/2 integral pi over 3 to pi over 2 of the same expression. And so the 2 and the 1/2 would cancel, and I would just have, for my area, pi over 3 to pi over 2, 16 sine squared theta minus 9 cosecant squared theta, d theta. Now, in terms of evaluating, I would definitely, if I had to evaluate the area, I would use this one. And if you had to go ahead and evaluate this, this is not a bad integral, you're going to use half angle on this one. And then this one's easy because you know a trig function whose derivative is negative cosecant squared, and that would be cotangent. Okay, let's do one more setup. Here we are going to use symmetry. Set up an integral for the area inside the circle, which is in red, r equals -2 cosine theta, and outside the circle, which is in blue, r equal 1. So when I set up my integral, if I imagine a ray going out from the origin, little r is the first curve I hit, big R is the second curve I hit. So my big R is going to be the circle in red, and my little r is going to be the circle in blue. Okay, I need limits. I want to find this angle right here. And I'm going to integrate from that angle to pi because I'm going to find the area of this dark green region and multiply my answer by 2 to get that whole crescent moon shape. All right, so first thing I want to do is set -2 cos theta equal to 1. That gives me cos theta is -1/2. So theta is going to be 2 pi over 3, 4 pi over 3, dot, dot, dot. The angle I want is in quadrant 2, that's 2 pi over 3. 4 pi over 3 is down here when they meet again. So my integral is going to be 1/2. First I'll set it up without symmetry, then I'll set it up with symmetry. 1/2 integral from 2 pi over 3 to 4 pi over 3, big R squared, which is 4 cosine squared theta, minus little r squared, so -1 d theta. Now I'm going to use symmetry, so now I'm going to take 2, multiply by 1/2, and just go half the way around. 2 pi over 3 to pi, same expression. And so these will cancel, and I'll just get 2 pi over 3 to pi, 4 cosine squared theta minus 1 d theta. And again, not a hard integral to evaluate. Most of the challenge here is in the setup. All right, and that is the end of this section.